All right, ladies and gentlemen, so here is just a video to sort of help and to go along with the notes that you should be seeing right up above. I'm not going to go through all of those sort of definitions of distance, speed, velocity, displacement. You can read about those. We'll sort of put them into place, but I do want to do a couple things here in this video. And the first is to just lay all of those concepts out in a little bit of a better way. So we've got scalars and vectors. Remember that a scalar only requires a magnitude, so mag only, and a vector requires a magnitude and a direction. We have to say where these vectors are going. Are they going north or south, up or down, left or right, wherever? And a lot of the scalars sort of have parallels that are vectors. So for instance, we've got distance as a scalar, and we've got displacement as a vector. And they've got parallels. They're both measuring amounts of length. Just remember that distance is how far you went. So that would be your odometer in your car, whereas displacement is just how far you got. So it would be, as the bird flies, right? There's no turns, none of that matters. It only matters where you end up. This is represented by delta x. We can break that down into the position final minus the position initial. And distance is just represented as a lowercase letter d. Beyond distance, we sort of take it one step further and we go into speed, which parallels with velocity. Your speed is how quickly you covered that distance. So that would be in meters per second. I'm going to write that over here instead, meters per second, because it applies to both of them. They're both an amount of distance over time, a rate of change of meters, of how much length. Speed is represented by the letter S, whereas velocity is represented by the letter V. So we could say that for both of these, speed is just an amount of distance over how long it took, and the velocity is just the displacement over how long it took. And we can break that up one step further. Sometimes instead of giving you the change in position, I'll give you the two individual positions, the initial and final, and you just sort of have to do this displacement piece first and then put it into that equation. And last but not least, and this isn't really in the notes up above, but we talked about it in class, we also have as a vector acceleration. And just like we had our velocity, which was a measure of displacement over time, our acceleration, which is represented by the lowercase letter a, is going to be our change in velocity over time. This is how much we changed, how fast we were going. So if we go from going 4 meters per second to the north, and then we end up at the end of some amount of time going 8 meters per second north, we had a change in velocity. Our speed changed. Either we sped up, we slowed down, or remember, because velocity is a vector, we can also change direction. Acceleration is speeding up, slowing down, or changing direction. We'll talk about that more on that next page. We've got a whole separate thing just on acceleration. But acceleration is a change in velocity over time. It's measured in units of meters per second, right? We're changing our velocity over some unit of time. It can also be written as meters per second squared. So let's go ahead and do a sample problem or two to sort of really solidify what the difference between this distance, displacement, and speed velocity is. So let's say that we had the Blue Valley High School football field, and it's measured in yards. We've got the 50-yard line here. And all in all, the distance here is 100 yards. And the one side of the field points north and the other points south. So let's say that one of our wide receivers, I don't even know who's playing this year yet because it's actually before the school year while I'm recording this. So let's say that we had a receiver that ran a route. He ran, let's say 40 meters, 40 yards. We'll do it in yards. And then let's say he cut up the field. Actually, I don't want to do that because that is actually for the next unit. So we'll erase that. And then he did sort of a cut back route. So he actually turned straight back around. We just want to do it in one direction. We just want it sort of in a straight line. We don't want to go up at all. So let's say he runs 40 yards out and he cuts back 10 yards, catches the ball, and then runs for another, let's call it another 40 yards. And this whole process, this whole play, but from the time that the ball was snapped, he starts running, and then he gets tackled near the end zone. Let's say that the time was 22 seconds. So from this, I want to know 4 things. I want to know his distance, his displacement, his speed, and his velocity. So remember, distance is just how far he went. And the easiest way to do this is just count up all of these little legs, 40, 40, and 10. We don't have to do anything because we're just worried about how far he ran. If he was going to just do all of that in a straight line, he would have gone 40 yards plus 40, I can't write, plus that 10 from the middle. So his distance was 90 yards. Notice that I include a unit. I don't need any direction though, because honestly, our direction changed in the middle there. But we just make everything positive, and we just add up those individual legs of his journey. For displacement, it's a little different. We actually have to assign a direction, sort of a positive or negative, to each one of these legs. So I like to make towards the right positive. It's just the way I was raised. So I'm going to say that to the right, that 40 yards is positive, but then he lost those 10 yards. He had to cut back. So he has a negative 10 yards and then another positive 40. So when I want to know how far I actually got from this point to this point, I have to do 40 yards minus 10 yards because I came back. If I had just stopped here and measured from this point to this point, that would only be 30 yards away. So I have to do a negative here and another 40 yards. So I've got 40 minus 10 plus 40. That is only 70 yards. And because this is a vector, right, I have to say which way did he go? Did he end up 70 yards north or south? And in this case, north. Notice that those two numbers are different, and distance is almost always going to be bigger than displacement. In fact, it is impossible for a displacement to be bigger than a distance. If your numbers come up that way, something went wrong. You might have got them flip-flopped. Distance and displacement can be equal, but that only happens if whatever object or person you're talking about when in a straight line didn't change directions at all the entire time. You can never have a displacement that's bigger than your distance. So let's go now into speed and velocity. We've already done all the legwork. Now it's just a matter of putting in our numbers to those equations and picking the right ones. Remember, speed is distance over time. So I'll take 90 divided by 22. That's going to come out to be about 4.9. We'll call it yards per second. Again, 9 times out of 10, we're going to be dealing with meters, but I'm going to keep my units consistent. We do need a distance unit, so in this case, we were using yards over our amount of time. And velocity, remember, is just displacement over time. So here we've got 70 divided by 22, and that's about 3, call it 3 1/3-ish. I don't know if that's quite right, but it's close. And again, that's yards per second, but this time with velocity again, I need a direction. It is a vector, and whatever direction my displacement is, my velocity is going to be in the same direction. Time doesn't have any sort of direction to it, it's just time. So whatever direction we had for our displacement, we also need it for our velocity. One of the questions that some people like to ask, and I like to ask, is let's say we had a rocket ship. I'm a terrible artist. And we've got nose cone blasting off. And it goes up into space. Come on. So it goes up into space, gets up there, stuff starts falling off, turns back around, and comes back down and actually lands on the exact same place. So let's say here's Florida. So it launches from Florida, goes up into space, goes around the Earth like 5 times, orbits for a while, and then it comes back down and it lands in the exact same place. Which was bigger, the displacement or the distance? You might say, well, it's got, look how far it went. And you're right, the distance is great. The distance is massive. But in this case, our displacement is 0. Our displacement was actually 0. The reason for that is the position that the ship ended up in is exactly equal to the position that it started in. It went from one place, did a bunch of stuff, but then it ended up in the exact same place it was before, meaning that it didn't actually get anywhere. Think of displacement as where did I get to? How far did I get? So because of that, the speed is big. But if my displacement is 0, that means my velocity is also 0. So next time you get pulled over by a cop, not that you would, you might, said, do you know how fast are you going? You might say, well, my velocity was this speed. He's like, well, my radar gun said it was, I don't know, 65 going down Null. Probably, I've seen you. You say, well, that might have been my speed, but my velocity, I was actually about home. So if you take my displacement divided by the time I'd been driving, I mean, heck, it'd been, 20 minutes. I went to McDonald's and came back. My velocity was pretty low. He's going to give you a ticket, but you'll still be right. And I'll probably give you a bigger ticket for doing that. So I wouldn't recommend it, but it's just some food for thought. So next time we'll talk about acceleration. We'll start talking about those changes to our velocity.